Let's figure out how to evaluate trig functions and get a formula for an answer. All right, and let's talk about why that is important. Let's say we wanted to figure out inverse sine of 1/2 and we weren't given any sort of range. What would the answer be? Well, let's pull up our unit circle and let's look at 1/2. Where is sine equal to 1/2? Well, we know it's true at 30 degrees right here. We know it's true at 150. Sine is 1/2. But what if we just keep going around the circle? Okay. If we had a 360 to 30, we'd be at 390 degrees. So it would actually be 360 and then back again to 390. Is it also equal to 1/2? Well, yes, it is. And if we kept going over here, so it'd be adding 120. So that'd be 410 degrees. It would also be equal to 1/2 at 410 degrees. And if we kept rotating, we'd get more and more and more and more angles. We can't write all those angles out, so we need to figure out a way of writing a formula that will encapsulate all those angles, which is the gist of this lesson. Okay? So more or less, we're finding a pattern of the angles and writing a formula for that. Most of the time, it's going to be in radians. All right, remember what an inverse trig function means. You plug in a ratio, you get an angle back. In this case, your answer will be a formula which will give you a multitude of angles. Don't forget these inverse trigonometric reciprocal identities, particularly if you're trying to figure out cosecant, secant, or cotangent, you would use these three identities. Example 1, write a general formula, and that's the key word here, a general formula for sine inverse of 1/2. Okay, so we know it's true at pi over 6. We know it's true at 5 pi over 6. How can we write a formula for that? Okay, well, make sure it's in terms of sine, cosine, or tangent for step 1 like we've been doing. We know it is. Now we want to determine the coordinates on the unit circle where this is true. We just said it's at pi over 6 and 5 pi over 6, or 30 and 150. Now, we know the angle is just going to keep, if we keep rotating the circle, we can generate more and more angles that make this true. For example, if we add 2 pi to pi over 6, that would be rotating 360 degrees. It would look like this. Okay, and we'd get, let's see, 13 pi over 6. Basically, adding 2 pi is adding 12 pi over 6. Okay, so we can kind of see that would be the next angle in our unit circle that would make, that would also be 1/2. Okay, and going back to our unit circle, going back to what I had before. Let's see, wrong one. Okay. If I move this over a little bit, if I can. I don't know if I can. Yeah, okay, here we go. Well, anyway, let's see. We'll just make a new one. Okay, so here's what we're talking about. All right, so that angle right there is 13 pi over 6. Okay, and we can tell off the bat. How did it generate? Oh, that's why I moved over. Okay, let's try this again. All right. So this angle right here at 30 degrees is the same as pi over 6. It's the same thing as 13 pi over 6. And we can see that the y value is 1/2, right? At 13 pi over 6 also. Right. So then we just need to figure, okay, what's the next angle after that in terms of pi over 6 that works? In other words, the coterminal angle of 5 pi over 6. So we'd add 2 pi to 5 pi over 6. Basically, for step 4, what we're saying is you want to add 2 pi to each of those angles you figured out on the standard unit circle. So now we're going to add 2 pi to 5 pi over 6. And 5 pi over 6 plus 2 pi is going to give you a coterminal angle of 70 pi over 6, which is this angle right here. So if you were to add 360 to that, you'd end up at the same angle, and that would be 17 pi over 6. So now we should have 4 angles. All right, 4 angles total. Now the question is, with these 4 angles, does it have a pattern? Okay, is there a pattern that we can write all 4 of these? And sometimes the answer is yes, sometimes the answer is no. You want to look at the spacing, particularly in the numerator, since they're all over 6. It goes 1, 5, 13, 17. The spacing's different, right? This one's 1, this one's 5, so the difference is 4. The difference between these two is 8, and then back to 4. So it goes 4, 8, 4. The pattern's not quite as easy as you might think. When the common difference isn't the same, we will write two formulas. All right? We'll write two formulas. So basically, the first and third will be part of one formula because you're just adding 2 pi to get there. And then the second and fourth will be part of another formula. Now, when the spacing's the same, you can write the same formula. That's ideal. Third term in the sequence will be one formula because the common difference between them will always be 2 pi. So we will write, basically, the next term after 13 pi over 6, if you were to add 2 pi, would just be 12 pi over 6 more, which would be 25 pi over 6. So how do we write that as a formula? Well, going back to common difference between an arithmetic sequence. Okay, the common difference between these coefficients is 12, right? Everything else is pi over 6, so we're only worried about the coefficient of pi. Common difference is 12, and the first term is 1. So in our formula for arithmetic sequence, if you haven't studied this, go ahead and watch that video on arithmetic sequences and finding the nth term and a general formula for it. First term is 1, a sub 1 is 1, common difference is 12, so the formula would be a sub 1 plus d times n minus 1, 1 plus 12 times n minus 1, so then you would distribute the 12n into the 12 into the n and 12 into the minus 1, so it would be 1 plus 12n minus 12. The 1 and the minus 12 combine to minus 11, so in general that means each of these coefficients can be simplified to 12n minus 11, and again the pi over 6 stays the same. So that's one of our formulas, okay? It's not the only one, it's one of them. This will also work for negative angles. So if you were to plug in, say, -3, it would give you a negative angle, something over 6, and that would ensure that the y value would also be equal to 1/2. For our other angles that we determine, 5 pi over 6 and 17 pi over 6, the next term would be 29 pi over 6. The common difference would be 12. We would use the same process to figure out that coefficient, okay, the pattern there would be 12n minus 7 pi over 6. So these two answers together are two formulas that will give you every single angle in existence that would ensure that sine is equal to 1/2 on the unit circle. Okay, not just angles within 0 and 2 pi, but angles that go on forever. Okay, and that's why we have formulas. All right, so that's it for this example. If you have any other questions about it or writing general formulas for trig inverse answers, let me know.